Welcome back. Tonight, we're going to do something simple and strangely comforting. We're going to watch probability being invented and then follow it as it changes through time. Not as a list of definitions and not as a fast lesson. We'll step into a few key moments in history quietly, when people first tried to measure uncertainty, how to split winnings fairly, how to reason about repeated trials, how to update belief when new evidence arrives, and how probability eventually becomes the language behind statistics, forecasting, and modern prediction. You don't need to remember anything, just listen and let the timeline move. We'll start at the point where chance stops being only a feeling and becomes something you can calculate. Let's go there now, candlelight paper and a question about fairness. We arrive in the middle of a practical problem. Two players are partway through a game of chance. They've both put money into the pot. The game is supposed to continue until someone reaches a certain number of wins, but it stops early. No one has officially won. So the question becomes very specific. Not who deserves the money, not who feels luckier. The question is, how do we divide the pot fairly based on where the game is right now? In 1654, this question travels in letters between two mathematicians, Blaise Pascal and Pierre de Fermat. Pascal is already known for his precise thinking about patterns and counting, ideas that connect to what people now call Pascal's triangle, and to his work on the arithmetical triangle, where counting combinations becomes almost mechanical. Fermat is known for his powerful number ideas, work that later includes Fermat's little theorem and the famous claim that becomes known as Fermat's last theorem. But tonight, they aren't proving those theorems. They're doing something quieter. They're trying to make fairness precise. The room is candlelit, ink on paper, careful language, and what they do is surprisingly calm. They don't try to predict the next result. Instead, they count possible futures. They imagine the game continuing from this exact point, and they list the different ways it could finish. And once you can list possible outcomes, you can compare them. Here's the soft idea underneath everything. If player A has more ways to eventually win than player B, then player A should receive a larger share of the pot right now. It isn't a guess, it's a ratio of futures. Let's keep it gentle and concrete. Imagine a match where the winner is the first person to win 3 rounds. Right now, player A has 2 wins. Player B has 1 win. So player A is 1 win away from winning the match. Player B is 2 wins away. From here, the match can end in at most 2 more rounds. Now we simply ask, what are the ways this can finish? There are 3 clean storylines. First storyline, player A wins the next round. The match ends immediately. Player A wins. Second storyline, player B wins the next round, and then player A wins the final round. Player A wins. Third storyline, player B wins the next round, and then player B wins the final round. player B wins. So from this position, there are three possible end stories. Two end with player A winning, one ends with player B winning. And if we assume each round is equally likely, then the fair split matches that ratio. Player A receives about 2/3 of the pot. Player B receives about 1/3. This is the early shape of probability, not a prediction machine, a fairness method, and you can hear their personalities in it. Pascal's side has that careful counting energy, like building rows of possibilities, the way Pascal's triangle organizes combinations. Fermat's side has that sharp, minimal logic, like his number arguments, but applied to everyday uncertainty. Now, one important observation. This reasoning quietly depends on an assumption that the next round is equally likely to be won by either player. In real life, that's not always true, but in games of chance, it's a reasonable starting point, and it makes the problem clear enough to calculate. What matters most is the method. They are building a habit that will return throughout history. 1. Define the possible outcomes. 2. Count them or weigh them. 3. Compare them. When you do that, chance stops being only a feeling. It becomes something you can reason about. Let's repeat the structure with one more example, just to make it feel stable. Imagine a match where the winner is the first person to win 5 rounds. Player A has 4 wins. Player B has 3 wins. From this point, the match can finish quickly, and again, there are 3 clean storylines. First, player A wins the next round. Player A wins the match. Second, player B wins the next round. Then player A wins the last round. Player A wins the match. Third, player B wins the next round. Then player B wins the last round. Player B wins the match. Again, 2 storylines lead to player A winning. 1 storyline leads to player B winning. So again, the fair split follows the same calm ratio. Now we zoom out slightly. This moment matters because it forces a new kind of thinking. Instead of asking who will win, they ask how many ways could each person win from this point onward. That shift is the seed of probability, and it begins here with a stopped game, a pot of money, and a question about fairness. Before we leave this moment, take one short line with you. When chance feels like chaos, the first step is to define the possibilities. And in the next moment in history, someone begins to write these ideas down in a form that can be taught, repeated, and used by anyone. We move forward from private letters to something more public. The question of chance leaves the desk drawer and becomes a small text that other people can learn from. We're now in the late 1650s, and the setting feels different. There's still a quiet desk, but now there's a booklet open with short examples written cleanly. The name we meet here is Christian Huygens. If you've heard his name before, it might be from physics and astronomy. He worked on the motion of pendulums and timekeeping, ideas that connect to the pendulum clock. He also has a principle named after him in wave theory, sometimes called Huygens' principle, describing how waves spread. And in the sky, he studied Saturn and discovered one of its moons, Titan. But in this moment, he's doing something calmer. He takes the new probability ideas, this counting futures approach, and gives them a teachable form. In 1657, he writes what is often described as the first published text on probability, a short work about reasoning in games of chance. And what makes it important is not drama, it's structure. He takes uncertainty and turns it into a method you can repeat. Now, instead of starting with a stopped game and asking, how do we split the pot, the focus shifts slightly. The new question becomes, what is a gamble worth on average? Not what will happen next, not what you hope happens, but what the situation is worth if you could experience it many times. This is where the idea of a fair value starts to settle into place, a calm average. And for a sleep-style explanation, you can picture it like this. If a gamble pays different amounts depending on what happens, you can think of its value as the balance point, the amount that would feel fair if the same gamble were repeated many, many times. And Huygens shows how to compute that fairness with simple reasoning. Let's keep it gentle. Imagine a very simple situation. A coin is flipped. If it lands heads, you receive one coin. If it lands tails, you receive nothing. So, over time, what is that gamble worth? Huygens' style of reasoning is to say, if heads and tails are equally likely, then in the long run you can expect heads about half the time. So on average, the payoff behaves like half of the one coin outcome, meaning the fair value is about half a coin. Now, we wouldn't actually trade with half a coin in your pocket, but the idea is what matters. You are turning uncertain outcomes into a single, calm number, a fair average. And that number becomes a new tool. It lets you compare gambles. It lets you decide what is fair to pay or fair to receive in exchange for a chance. And this is a quiet shift in the history. Earlier, probability begins as a fairness calculation for an interrupted game. Here, probability becomes a general method for valuing uncertain outcomes. You can feel the discipline forming. Now, there's a second important thing happening here. This booklet doesn't just give answers, it gives a way of thinking that other people can copy. Short examples, clear steps. It helps probability become a shared language, and once a language exists, it starts to spread. Now let's make the key idea feel even simpler and very speakable. When we talk about a fair value in this early probability sense, we are really saying, if I could watch this gamble unfold again and again, what would the average payout settle toward? That's it. That's the calm center. Now let's do one more example. still in words, no symbols needed. Imagine a wager where there is a 1 in 3 chance you receive 3 coins and a 2 in 3 chance you receive 0. The outcomes feel extreme, either 3 coins or nothing, but the fair value is the long-run average. Over many tries, receiving 3 coins about 1/3 of the time means the average outcome behaves like 1/3 of 3 coins, which is about 1 coin. So even though the gamble feels like all or nothing, the fair value sits quietly in the middle, around 1 coin. This way of thinking, taking a messy set of outcomes and compressing it into a calm average, becomes a backbone. And it also foreshadows something important about probability as it evolves. Probability isn't only about what happens, it's about what you should expect and how you should price uncertainty. Now we pause for a moment and make a careful historical observation. Huygens isn't inventing these ideas from nothing. He's building directly on what came through those earlier letters. The earlier work creates the seed, count futures to divide fairly. Huygens helps the seed grow into a method, a compact, teachable system for evaluating chance. And now, because it's written down clearly, other mathematicians can push it further. Now, let's bring the atmosphere back to your observation through time theme. We stand quietly behind him, watching him tidy up uncertainty. We watch him treat chance as something that can be handled calmly, and we notice a pattern. Every time probability advances, it advances by becoming more structured, less superstition, less gut feeling, more method. Now, a small moment of gentle repetition, because repetition is what makes this style sleep-friendly. Probability in these early decades is doing 3 steady jobs. 1. Dividing fairly. 2. Valuing uncertain outcomes. 3. Building a language that can be taught. And in this part of the timeline, we're focused on the second and third, valuing and teaching. Now we're ready to move to the next major change, because once you have a method for valuing gambles, the next natural question appears. It's a question about time and repetition. It goes like this. If chance is messy in small samples, does it become stable in large samples? If you repeat an experiment many times, do the results settle towards something reliable? This is where probability begins to connect to what we now think of as statistics and long-run behavior. And this is the next step in the timeline. So we move forward again from tidy book examples to a deeper idea that large numbers can smooth randomness into something predictable. We move forward again. We've seen chance used for fairness and then taught as a method for valuing uncertain outcomes. Now the next question arrives naturally, almost inevitably. If a few trials look messy, what happens when you repeat the same kind of trial many times? Does randomness stay wild forever, or does it begin to settle into something calmer? We arrive in the early 1800s, just slightly earlier than it sounds, because the key work we're observing is published in 1713. The name here is Jakob Bernoulli, and the work most closely tied to this moment is his book Ars Conjectandi, meaning the art of conjecturing. It's published after his death, but it carries a clear message. If you repeat a random experiment enough times, the results begin to stabilize. Not perfectly, but reliably. This is one of the first clear statements of what we now call the law of large numbers. Now, we keep this sleep-friendly by treating it like an observation. Imagine we are standing in a quiet lab, no machines, no noise, just a coin, a notebook, and time. The coin is fair. Heads and tails have the same chance. But if you flip it only a few times, the story can look strange. You might see 3 heads in a row or 5 tails out of 6 flips. And if you're anxious, the mind starts trying to interpret it. It means something. It's a sign. It's changing. But Bernoulli's key insight is calmer than that. Short runs are noisy, long runs are steady, and the way to see it is to stop thinking in terms of what happens next and start thinking in terms of proportions. So we don't focus on the raw sequence, we focus on a single quiet measurement. Out of all flips so far, what fraction were heads? Now imagine we begin. We flip once. If it's heads, the fraction of heads is 100%. If it's tails, the fraction of heads is 0%. In other words, after one flip, the fraction can be extreme. Then we flip again. Now the fraction of heads can be 0%, 50%, or 100%. Still extreme, still jumpy. But something changes as the minutes pass and the count grows. As the number of flips becomes large, each new flip has less power to swing the overall fraction. The fraction begins to move more slowly. It wobbles, but the wobble shrinks, and over time it tends to hover around 1/2, not because we forced it, not because we controlled it, but because the averaging effect of many trials smooths the randomness. This is the feel of the law of large numbers, and it's a genuinely calming idea because it says randomness can look dramatic in small samples, but it becomes more regular when you observe it over longer stretches of time. Now, I want to keep this factual and simple. Bernoulli's point is not that the fraction becomes exactly 1/2. It's that as the number of trials increases, the fraction gets closer to 1/2 and the chance of being far away becomes smaller. In plain language, large numbers make extreme outcomes less likely. Large numbers don't remove randomness, they soften it. Now we'll do a gentle time lapse in words. Imagine we flipped the coin 10 times. Maybe we saw 6 heads, so the fraction is 6 out of 10, 60%. Then we keep going. After 50 flips, maybe it becomes 27 heads. Now it's 27 out of 50, 54%. After 100 flips, maybe it becomes 52 heads. Now it's 52%. Notice the pattern. The fraction can still drift, but the scale of its movement slows down. It becomes less jumpy, more stable, and this is exactly what makes probability start to connect to the real world. Because once you trust long-run stability, you can do something powerful. You can estimate unknown chances by repeating experiments. You can observe frequencies and use them as information. This is one of the stepping stones from early probability to statistics. Now, let's connect it back to the history we've already observed. Earlier, we counted possible futures to split a pot fairly. Then we calculated fair values by thinking in long-run averages. Now Bernoulli ties those instincts together into a deeper statement. If you repeat a chance process many times, you can expect stable proportions, and you can build reasoning on top of that stability. Now we slow down and say it in one clean line twice because it matters. As the number of trials grows, the observed proportion tends to settle near the true probability. As the number of trials grows, the noise smooths out. Now there's another piece that belongs in the atmosphere of your video. This isn't only about coins, it's about any repeatable situation where uncertainty is present, weather patterns, manufacturing defects, measurements with error, human behavior in large groups. Bernoulli's insight is, when you have many observations, the big picture can become clearer than any single event. One event is noisy, many events reveal structure. Now, we take a quiet moment to prevent a common misunderstanding because your audience will feel it. Some people hear law of large numbers and think it means if I flip tails many times, heads is due. But that's not what it says. It does not say the next flip will compensate for the past. Each flip remains uncertain. What it says is something calmer. In the long run, the overall fraction tends to settle, not the next event, the long-run picture. So if you want a sleep-friendly phrase to carry forward, the next moment is unknown, but the long-run pattern becomes knowable. Now we watch the timeline move again. This idea, long-run stabilization, becomes a foundation. Because once you accept that frequencies can settle, the next question appears. If results cluster around a typical value, what shape does that clustering take? Do random outcomes have a geometry? Do they form a curve? And that curiosity leads us to the next step in the evolution, from stability over time to the quiet shape of randomness. So we move forward again, from long-run calm to the early appearance of the bell-shaped pattern that will eventually become central in probability and statistics. We move forward from the idea that large numbers make randomness steadier. Now a new curiosity appears. If repeated trials settle toward a stable proportion, then the results also tend to cluster. Most outcomes land near a typical value. Fewer outcomes land far away. So the next question becomes, what shape does that clustering take? We arrive in the early 1700s, and the name here is Abraham de Moivre. If you've encountered his name before, it might be through de Moivre's formula. a famous connection between trigonometry and complex numbers. But in this part of the timeline, we're watching his work on chance. He writes a major book called The Doctrine of Chances, and in 1733 he publishes a result that quietly changes the future of probability. The result is simple to describe, even without equations. When you repeat an event like coin tossing many times, the number of heads you get does not spread out evenly. It forms a pattern. Most of the time, you land near the middle. And the further you move away from the middle, the rarer it becomes. De Moivre notices that when the number of trials is large, this pattern begins to resemble a smooth, bell-like curve, a gentle hill, a single peak near the center, and long tails that thin out toward the extremes. This is an early step toward what later becomes known as the normal distribution, the bell curve. Now, we'll keep it grounded and observational. Imagine we're doing the calm coin experiment again. We flip a fair coin many times, let's say 100 flips. What's the middle result? The middle is around 50 heads, not because we forced it, but because half of 100 is 50, so the typical outcome sits near 50. Now think about how you might get exactly 50 heads. There are many sequences that lead there. Heads and tails can appear in countless orders and still add up to 50. Now think about an extreme like 90 heads. There are fewer sequences that lead there. It's not impossible, but it's rarer. And this is a key insight that connects back to Pascal's counting method. Probability often comes down to counting. How many ways can something happen? The middle has more ways to happen than the extremes. So the middle occurs more often. And as the number of flips grows larger, this more in the middle, less at the edges pattern becomes clearer and smoother. This is where de Moivre's contribution becomes especially important. He doesn't only describe the pattern, he shows you can approximate it. He finds a way to estimate how likely it is to be near the middle or far from it without having to compute every exact count. That matters because the exact counting becomes impossible very quickly. With 10 flips, you can count. With 100 flips, counting exactly becomes heavy. With 1,000 flips, it becomes absurd. So, de Moivre introduces something that will become a theme in probability. When exact calculation becomes too hard, you can use approximation. And the approximation has a shape, a smooth shape, a curve. Now, let's make this feel vivid without turning it into a math lesson. Picture a long wooden board with many pegs, like a gentle sorting machine. A single ball drops from the top. At each peg, it bounces left or right like a coin flip. After many bounces, it lands in one of many slots at the bottom. If you drop one ball, it lands somewhere random. But if you drop thousands of balls, you see a pattern. Most land near the center, fewer land far from the center, and the whole pile begins to form a hill. That hill is the feeling de Moivre is capturing. Randomness is not just chaos, it has structure, it has shape. Now we pause for one important clarification because it keeps this historically accurate and conceptually clean. De Moivre is working with the binomial setting, repeated trials with two outcomes, like heads or tails. The bell-like curve appears as a powerful approximation when the number of trials is large. It's not that the world is automatically a bell curve, it's that many repeated, balanced, random processes tend to produce a bell-like clustering, and that idea becomes unbelievably influential later. Because once you recognize that randomness often forms a curve, you can begin to measure uncertainty in a new way. Instead of only saying, "This happened," you can say, "How far from the middle was it?" And you can say, "How rare was that distance?" So now probability gains a new dimension, not just long-run averages, but the shape of variation around the average. Now, I'll say the key point in one clean line twice, because this is the moment it really lands. When you repeat a random process many times, outcomes tend to cluster near a typical value, and that clustering often follows a smooth bell-like pattern. Now we connect it back to the timeline. Pascal and Fermat define possible futures and count them to make fairness precise. Huygens teach probability as a method and introduce fair value as a calm average. Bernoulli show that repeated trials stabilize proportions in the long run. De Moivre show that repeated trials also produce a predictable shape of variation. This is a major expansion. Probability is no longer only about what's fair or what's expected. It's also about how results spread out, how they cluster, how they vary, and that becomes the doorway to statistics. Now, before we move on, we'll do one more gentle observation to make the idea feel complete. Imagine you're counting heads in 100 coin flips. Most of the time, you won't get exactly 50. You might get 48, or 52, or 46, or 55. Those are close to the center. They feel normal. But as you drift farther from 50, say 65 heads, the result feels surprising, not impossible, just rarer. So de Moivre's curve gives you a way to think about surprising as a measurable thing. Surprise becomes distance from the center, and rarity becomes the thinning tail of the curve. This will become essential later when probability starts guiding scientific measurement. When you see a result, you want to know whether it's ordinary variation or something meaningful. That question, ordinary variation or something meaningful, will define much of modern statistics. And it begins forming here, quietly, with this idea of shape. Now we take a breath and move the timeline forward again, because once you have a method for fairness, a method for expectation, a method for long-run stability, and a method for the shape of variation, the next step becomes natural, probability starts to shift from games and repeated trials to a deeper idea. How should belief change when new evidence arrives? Not just what happens in the long run, but what you should think now, given what you've observed. That is the next turning point in the history, from the shape of randomness to the logic of updating belief. We've seen probability used to divide fairly, to value uncertain outcomes, to stabilize in the long run, and to reveal a smooth shape around the average. Now the timeline shifts again, because there's another kind of uncertainty that matters in real life, not just what will happen next, but this: given what I've already seen, what should I believe now? This is where probability becomes a tool for reasoning with evidence. We start with a name that most people connect to a single idea: Thomas Bayes. Bayes does not publish a famous book during his lifetime. Instead, an essay appears after his death in 1763. And inside it is the core idea that later becomes known as Bayes' theorem. Now I'll say it in plain language first, because this style works best when it's gentle. Bayes' theorem is a rule for updating. It connects three things: what you believed before, what the new evidence looks like if your belief is true, and what you should believe after seeing the evidence. In modern terms, people often describe it like this: prior, evidence, updated belief, or even more simply, before, data, after. And the reason it matters is that it gives a structured way to change your mind, not emotionally, mathematically. Now, we'll keep this calm and concrete with an observation that could happen at night. Imagine you're listening for a sound outside. Before you hear anything, you already have a before belief. Most nights, nothing unusual happens. So your starting belief leans toward it's probably the wind. That starting belief is your prior. Then you hear a sound. That sound is evidence. Now you ask a careful question. If it really is wind, how likely is this kind of sound? And also, if it really is something else, say a person walking, how likely is this kind of sound? Bayes' theorem is the logic that connects those comparisons. It tells you how to adjust your belief without guessing wildly. And notice what's happening historically. Probability is moving away from games. It's moving toward knowledge, toward learning, toward inference. Now, I'll say Bayes' theorem one time in a spoken VO-friendly way. Bayes' theorem says, your updated belief is proportional to your original belief, multiplied by how well the evidence fits. That's the entire mood of it. You start with a baseline expectation, then you let the evidence nudge it. Now Bayes is the seed. The next major figure is the one who grows that seed into a system, Pierre-Simon Laplace. Laplace is known for many things: physics, astronomy, mathematics. You'll hear his name in phrases like Laplace's equation and the Laplace transform, and even Laplace's demon, the idea of perfect prediction in a perfectly known universe. But in probability, his role is especially important. Laplace takes the updating idea and builds it into a broad framework. He applies probability to scientific questions, astronomy, measurement error, population data, inference from observations, and he turns probability into something like a universal method, a way to reason when information is incomplete. Now, here's a key historical shift to make clear for your audience. Earlier probability often begins with symmetrical games, coins, dice, cards, situations where equally likely feels natural. But in real life, you don't always have symmetry. You often start with uncertainty about the underlying cause, and that's exactly the kind of uncertainty Bayes and Laplace address. They help probability handle hidden causes, not just visible outcomes. Now we'll do one more simple example, still in words, still calm. Imagine there are two coins on the table. One coin is fair, the other coin is biased and lands heads most of the time. You pick one coin without looking, you flip it once and get heads. Now ask, which coin do you think you picked? A single heads doesn't prove anything, but it does shift your belief slightly toward the biased coin. Then you flip again, another heads. Now your belief shifts more, not to certainty, just to a stronger lean. This is the Bayesian feeling. Beliefs move gradually as evidence accumulates, and Laplace helps make this style of reasoning usable in broad settings. It becomes a way to learn from observations. Now I'll compress the historical takeaway into one clean line twice. Probability becomes not only the math of chance, but the math of learning from evidence. Probability becomes a method for updating belief step by step as information arrives, and once that idea enters the story, the timeline opens up. Because the moment probability becomes a tool for measurement, science, and inference, it starts to appear everywhere. In repeated experiments, in error and noise, in population data, in decisions made under uncertainty, and the next step in the evolution is exactly that. Probability leaves the gaming table almost completely and enters the laboratory, the observatory, and the world of measurement. So now we move forward again from updating belief to understanding error, noise, and uncertainty in real observations. We move forward from belief updating into something more physical. Because once probability becomes a way to learn from evidence, the next problem is unavoidable. Real measurements are never perfectly clean. You measure the same thing twice, and you get two slightly different numbers. So the question becomes, how do we describe error without panic? And how do we extract a reliable signal from noisy observations? This is where probability steps fully into science. We begin in the world of astronomy and precision measurement. The name you'll hear here is Carl Friedrich Gauss. Gauss is famous across mathematics, but in this part of the story, his role is simple. He helps formalize the idea that measurement errors often cluster around a central value, with small errors being common and large errors being rare. This is the bell-shaped pattern showing up again now as a practical tool, and alongside that, Gauss becomes closely connected to the method of least squares. Least squares is a calm rule for fitting a model to noisy data. It says, in effect, when your observations don't line up perfectly, choose the explanation that makes the overall discrepancies as small as possible, especially avoiding large errors. It's a way to treat noise as something expected, not something shameful. Now we pause and observe what changed. Earlier, probability was often about games or abstract chance. Here, probability becomes a tool for measurement, a method for working with imperfect instruments and imperfect observations. And then the same probabilistic thinking begins to spread into society. We step into the 19th century and we meet Adolphe Quetelet. Quetelet applies probability ideas to human data, things like heights, crime rates, and social patterns. He becomes known for the idea of the average person, what he called l'homme moyen. Whether or not we like that framing today, historically it matters because it pushes probability outward. Not just coins and planets, but populations. And once you start measuring populations, variation becomes unavoidable. You can't describe a population with a single number. You also need a language for spread, for typical values and deviations, for clustering and tails. Probability provides that language. Now we move further into the late 1800s and we meet a name that becomes central to modern statistics, Francis Galton. Galton studies heredity and human traits, and he becomes strongly associated with two ideas that will echo through the future. The first is correlation, the idea of measuring how strongly two quantities move together. The second is regression toward the mean, a phrase that comes from his observations that extreme values tend to be followed by more typical values, not because nature is correcting things in a moral way, but because variation plus inheritance tends to pull extremes back toward the average. And here is the big historical shift you want your audience to feel. Probability is no longer only about chance events happening. It's about patterns in data. It's about measurement. It's about relationships between variables. It's about describing a world where uncertainty is normal. Now, let's make the thread clear and sleep-friendly. Across the 1800s, probability gains three practical roles. 1. It becomes the language of measurement error. 2. It becomes the language of populations and variation. 3. It becomes the language of relationships like correlation. And once those roles exist, the next step is almost inevitable. Because if probability can describe error and describe variation and describe relationships, then it can also guide experiments. It can help us decide whether an observed difference is meaningful or just noise. And that brings us to the next era, the early 1900s, where statistics becomes a formal toolkit for testing ideas in the real world. So now we move forward again, from measurement and variation to experiments, evidence, and the disciplined question, how sure are we? We move into the early 1900s. Probability is no longer just a way to think about games or long-run averages or measurement error. Now it becomes something even more practical, a toolkit for drawing conclusions from data, a toolkit for answering questions like, is this effect real? Or is it just noise? We begin with Carl Pearson. Pearson's name is attached to tools that many people still use today. He helps formalize the idea of measuring association with the Pearson correlation coefficient, and he introduces methods for comparing observed data to an expected pattern, including the chi-squared test. What matters historically is the shift in attitude. Instead of treating variation as a problem to ignore, statistics treats variation as the central object. You don't hide the noise, you measure it. Now we step to another key figure, often known by a pen name, student, the statistician William Seeley Gossett. He develops what becomes known as the t-distribution, designed for situations where sample sizes are small. And this is important because small samples are common in real experiments. In plain language, this part of the timeline says, if you don't have much data, you need methods that understand that uncertainty is larger. Now we arrive at a name that reshapes modern statistics, Ronald Fisher. Fisher's contribution is broad, but tonight we keep it clean and VO friendly. He develops methods for estimation, including maximum likelihood, which is a way of choosing model parameters that make the observed data most plausible. He develops analysis of variance, often called ANOVA, which helps separate variation into different sources. And he becomes deeply associated with experimental design, how to set up experiments so that randomness helps you instead of confusing you. This includes ideas like randomization, control groups, replication. This is a huge moment in the story because probability is no longer only describing uncertainty after the fact. It is actively shaping how we gather evidence. Now we pause for a calm summary because this part is easy to overcomplicate. In the early 1900s, statistics becomes a disciplined way to answer, if I see a pattern in data, how confident should I be that it isn't just chance? And the core strategy is consistent. You compare what you observed to what you would expect under randomness. You ask whether the observed result is unusually far from what chance alone would typically produce. That's the basic logic behind many statistical tests, even when the details vary. Now let's connect it to the thread of the whole video. Earlier we learned that large numbers stabilize proportions. Then we learned that randomness has a shape. Then we learned how belief can be updated with evidence. Then we watched probability enter measurement and society. Now we see probability become a tool for experiments, a way of deciding what the data really supports. And after this, the next step is almost unavoidable, because once probability is used everywhere, people want it to be perfectly clear what probability is mathematically. They want a clean foundation, a small set of rules that everything else sits on. So now we move forward again, from practical methods to the moment when probability is given a formal axiomatic base. We move forward to a quieter kind of progress. Up to this point, probability has grown through problems and methods, games, long-run behavior, measurement error, experiments, and inference. But now mathematicians want something very specific. They want a foundation, a way to say clearly and universally what is probability exactly as a mathematical object. What are the basic rules it must follow no matter the application? We arrive at 1933, and the name here is Andrei Kolmogorov. The work associated with this moment is his book, usually translated as Foundations of the Theory of Probability. Kolmogorov's contribution is not a new trick for coins or cards. It's a clean framework that can hold everything we've seen so far, and he does it with a small set of axioms, basic rules. Now, to keep this sleep-friendly, we'll treat it like setting up a simple observation space. Imagine we're back in our quiet room, but this time, before we run any experiment, we prepare three things. First, we define the full set of possible outcomes. This is the world of possibilities for the situation. In modern language, it's called the sample space. Second, we decide what kinds of outcomes we're going to talk about. Not every tiny detail, just the events we care about. For example, heads, or at least 60 heads, or a measurement within a certain range. These are called events. Third, we assign a probability to those events in a consistent way. That assignment is called a probability measure. And now come the rules. Kolmogorov's axioms are often stated in a short list. I'll say them in a way that sounds natural out loud. Rule 1. Probabilities are never negative. You can't have less than 0 chance. Rule 2. The probability of the entire sample space is 1, meaning something in the world of possibilities must happen. Rule 3. If two events can't both happen at the same time, the probability of either one happens is the sum of their probabilities. So if two events are mutually exclusive, no overlap, then A or B is just A plus B. That third rule is the one that quietly powers a lot of probabilities machinery, because it formalizes what we've been doing since the beginning, taking a collection of possible outcomes and adding them up in a disciplined way. Now, there's an important detail here, stated gently. Kolmogorov's framework isn't only about adding two events. It extends to long lists of events as well, so probability can handle complicated situations with many possibilities. That's one reason this foundation becomes so powerful. It doesn't care whether you're working with dice, measurement error, random processes, or statistics. If you can define the outcomes, define the events, and assign probabilities obeying those rules, you have a valid probability model. So this is the historical turning point. Probability becomes fully general, not tied to gambling, not tied to any single interpretation, just a consistent mathematical structure. Now I'll compress the takeaway into one clean line twice. Kolmogorov turns probability into a rigorous system, outcomes, events, and a consistent assignment of chance. With a few simple rules, probability becomes a stable foundation for everything built on top of it. And once that foundation is in place, the next leap becomes easier, because now probability can confidently expand into time-dependent systems, processes that evolve step by step, and into computation, where we simulate randomness when exact calculation is too hard. So now we move forward again from foundations to probability in motion, probability in machines, and probability powering modern prediction. We move forward from foundations into motion, because once probability has a rigorous base, it can comfortably describe not just single events, but systems that evolve over time. This is where probability becomes dynamic. One of the key names here is Andrei Markov. Markov's work introduces what we now call Markov chains, a simple but powerful idea. Sometimes, to predict what happens next, you don't need the entire past, you only need the present state. In spoken terms, a Markov process says the next step depends on where you are now. That idea becomes a backbone of modern modeling, especially for sequences, weather patterns, cues, text, signals, and many other processes that unfold step by step. Now we step into another major shift. Probability meets communication. The name here is Claude Shannon. In 1948, Shannon's work helps launch information theory, and probability becomes central to it because information is deeply tied to uncertainty. If something is very predictable, it carries little new information. If something is surprising, it carries more. This connects probability to messages, signals, compression, and noise. In other words, probability becomes part of the infrastructure of the modern world. Now we move into the era where probability becomes computational, because many probability calculations are too complex to do exactly. So instead of solving them on paper, we simulate them. This is where the Monte Carlo method enters the story. The basic idea is beautifully simple. If you can't compute the answer directly, you can approximate it by running many random trials and observing the average result. You let randomness run many times, and you measure what it tends to do. This becomes essential in physics, engineering, finance, and risk analysis, anywhere the system is too complicated for neat formulas. And now we arrive at a modern theme that ties everything together. Probability becomes the language of prediction under uncertainty. Not prediction as certainty, but prediction with error bars, prediction with confidence, prediction with humility. Through the late 20th century and into today, probability shows up everywhere, in filtering and tracking, like the Kalman filter, which estimates a changing system from noisy measurements, in medical studies and evidence-based decisions, in forecasting from weather to economics, and in machine learning, where probability helps models express uncertainty rather than pretending they know everything. Now, I want to say one clean line that keeps this historically consistent with everything we've observed. Over time, probability evolves from counting futures to measuring variation, to updating belief, to modeling systems, to powering modern prediction. And it does it without removing uncertainty. It makes uncertainty usable. Now we come to the present moment. We live inside probability every day, often without noticing. When an app predicts a route time, when a forecast gives a chance of rain, when a medical test result is interpreted, when a model estimates risk, all of these are probability in its mature form, built on the timeline we just walked through. And now we begin to gently land this, because the goal tonight wasn't to memorize, it was to observe. So here's the quiet summary, spoken slowly. It begins with fairness. It becomes teachable. It becomes stable in the long run. It reveals a shape. It learns to update belief. It enters measurement and society. It becomes a toolkit for experiments. It gains a formal foundation, and then it moves into time, information, simulation, and modern prediction. And through it all, probability remains what it always was, a calm way to reason when we cannot fully know. Now, if you're sleepy, you can let the timeline fade. And if you're still awake, we can drift back through the key moments once more, slowly, without adding anything new. We'll return to the beginning and simply watch the idea appear again. And that brings us back to the present. Tonight, we didn't try to memorize formulas. We simply watched an idea grow slowly across time, from a question about fairness in a stopped game, to teachable methods and long-run stability, to the shape of randomness, to updating belief with evidence, to measurement, experiments, foundations, and finally to simulation and modern prediction. Probability never removed uncertainty. It gave uncertainty structure. If you're still awake, you can let these moments replay in your mind like a quiet timeline. And if you're ready to sleep, you can let the details soften. Thank you for being here. And whenever you like, you can close your eyes and let the history fade into the background.